Welcome to the next video in our 5G waveform series, where we focus on the synchronization signal block. In this episode, we'll explain what the SSB is and where it's located within the OFDM grid. We'll also continue our 5G transmitter implementation using MATLAB's 5G toolbox by introducing the SSB burst configuration. Let's get started with the first section. The synchronization signal block is a constantly broadcasted element of the 5G downlink waveform. It occupies 4 OFDM symbols in time and spans 240 subcarriers in frequency. The SSB contains 3 main components. Primary synchronization signal is used for initial time and frequency synchronization. It supports 3 different sequences, each occupying 127 subcarriers. Secondary synchronization signal is transmitted in the second OFDM symbol and supports 336 different sequences. Together with the PSS, it enables the UE to determine the physical cell ID. Physical broadcast channel occupies the remaining resource elements within the SSB. It carries essential system information, including the master information block, which is critical for the UE to initiate a connection with the cell. Now, let's look at when SSBs are transmitted in the time domain. 5G supports the use of multiple beams for downlink transmission. Each beam transmits its own SSB, but at different OFDM symbol positions, so that signals from different beams don't overlap at the receiver. This helps the UE distinguish between beams during the initial access procedure. These SSBs are grouped into SS bursts, each lasting 5 milliseconds. The entire SS burst is then periodically retransmitted based on a parameter called the SSB period, which by default is set to 20 milliseconds. Additionally, 5G SSBs can follow different transmission patterns. In FR1, there are 3 defined options: case A, B, and C. Each case specifies a different subcarrier spacing, 15 kHz for case A and 30 kHz for cases B and C. The chosen pattern also determines the possible OFDM symbol positions of the SSBs within a frame. Now, let's examine the SSB frequency position. In LTE, the PSS, SSS, and PBCH are always transmitted at the DC carrier frequency. In contrast, 5G allows the SSB to be shifted in frequency by a parameter known as the subcarrier offset. The selection of the carrier frequency is also constrained to specific predefined positions, identified by the absolute radio frequency channel number. To determine the exact SSB frequency position, the UE must search across all possible locations relative to the given carrier frequency. To simplify this process, the Global Synchronization Channel Number was introduced, providing a raster that defines the set of valid frequency positions where an SSB may be located. In the second section of this video, we demonstrate the SS burst configuration using the MATLAB 5G toolbox. We'll continue building on the transmitter implementation from our previous video on the 5G downlink waveform. If you haven't seen that video, we recommend watching it first or downloading the corresponding code using the link provided below. We begin by adding a new parameter in the configuration section, the signal bandwidth in megahertz, and initialize it to 10. This parameter will control the bandwidth of the generated signal. Additionally, we've included a function called Maximum Transmission Bandwidth Configuration, located in the Utilities folder. This function returns the number of resource blocks corresponding to a given bandwidth and subcarrier spacing, based on 3GPP specification, as shown on the slide. Now let's switch to the configuration file and begin by adding the new bandwidth parameter. We also create a new section specifically for SSB configuration. In this section, we set the SS burst option of the NR configuration using a custom SSB function. Within this function, we start by creating the SSB configuration using the nrWaveformGeneratorSSBurstConfig object from the 5G toolbox. We then define the transmitted blocks parameter, which specifies which SSBs are active within a burst. Next, we set the burst period to 20 milliseconds, the default value. We also configure 2 additional parameters: DMRS type A position, which determines the position of the DMR symbols in the PDSCH, and the PDCCH SAB1 position. These 2 parameters will be covered in more detail in future videos. Finally, we configure the SSB block pattern and subcarrier spacing. To retrieve the appropriate subcarrier spacing from the configured SSB case, we use a custom utility function. As shown, the values align with the theory presented earlier. Let's also go over the final utility function, synchronization raster. This function generates all possible SSB frequency positions based on 3GPP specification. It then filters out the positions that do not fit within the configured bandwidth and converts the valid ones into subcarrier offsets relative to the carrier frequency, expressed in multiples of the subcarrier spacing. Now, let's return to the SSB configuration. Using the synchronization raster function, we generate the possible subcarrier offsets based on the given carrier frequency and bandwidth. In this example, we select the offset closest to the carrier frequency, specifically subcarrier 0. Next, we compute the numerology from the specified subcarrier spacing. This is required to determine the center subcarrier of the bandwidth, measured from common reference point A. In FR1, this reference is always expressed in multiples of 12 subcarriers at 15 kHz subcarrier spacing. If we use this value directly as the SSB position, the SSB would be centered in the middle of the allocated bandwidth. However, our goal is to offset the SSB by the previously defined amount. To do this, we first convert the offset into multiples of 12 subcarriers and apply the numerology to ensure it is consistently referenced in terms of 15 kHz SCS. Finally, we apply this offset relative to point A in the SS-burst configuration. Since the step size here is 12 subcarriers, we also set the KSSB parameter, which allows fine-tuning of the SSB position within the selected resource block. With the SSB configuration complete, we return to the main configuration file. To ensure the code correctly generates the 5G downlink waveform, we also need to define the carrier and bandwidth part configurations. We use the same subcarrier spacing as the SSB for other channels and allocate all available resource blocks within the specified bandwidth. The SCS carriers and bandwidth parts parameters are then configured using predefined helper functions. These functions simply create configuration objects and assign values for subcarrier spacing, the number of resource blocks, and the starting resource block. In the final part of the main configuration, we disable the physical downlink control channel by setting its enable property to false, since this video focuses only on SSBs. Now we run the transmitter code to generate the waveform. As shown, 4 SSBs are transmitted according to the transmitted blocks parameter, and the entire SS burst is slightly shifted in frequency to align with the calculated synchronization raster offset. We can also increase the number of generated subframes to 25. This example demonstrates how SS bursts repeat with the configured 20 millisecond period. And that's it for this video. If you want to keep exploring 5G waveforms and learn how the UE receiver uses PSS and SSS for time and frequency synchronization, be sure to watch the next video in the series. Thanks for watching.